Namaskar. So now we have seen that what is determinant and how to expand the determinant, how to get the determinant of a matrix and for the different orders of the matrix, how to expand and how to calculate, how to determine the value of a determinant. So here now, as we discussed in a previous lecture, that the best way to minimize the calculations and get the efficient result in a much lesser time, you always try to expand it through the row or column which have a maximum number of 0, right? So here we are going to see some properties where how we can achieve that maximum number of 0 without affecting the determinant values, and then we can expand that, and that definitely improve and the efficiency of or the time required to estimate the values for higher order determinants. So let's see what are those properties and some tricks that how we can easily solve and simplify our calculation, which sometimes becomes much laborious. We have to spend lots of time to solve that, and utilizing the techniques and properties you can easily solve those in a fraction of 10 minutes, right? So let's see those properties. So the first property states that the value of a determinant remains unchanged if its row and columns are interchanged, meaning that let's say if this is a determinant and the value here, let's say represent right now a1, a2, a3, b1, b2, b3, and c1, c2, c3, right? Now it says that first let's find out the value. As the statement says that if I interchange any if any row or column is interchanged, for example, let's say this is your C1, this is your column C2, and this is your column C3, and this is your column row 1, and this is your row 2, and this is your row 3. So interchange row 2 or row 3 or row 1, row 2, or you interchange C1 with C2 or C2 with C3, the value will not change, the determinant will remain same. So let's see what we get. So for example, if you calculate this and then how you'll expand it, so you will get here this is a11, right? The index is 11, so it will have minus 1 to the power 11 is square, so it will have plus, and then you will left with that. So you remove this and then you will get these right here. So b2, b3, c2, c3. Now here it will be minus for this element. I am expanding with respect to r1 here. So a2 and then you will get this minus is that because this is the index of 1 2, so it will have minus 1 to the power 3, so minus 1, right? Minus a2, and you will leave this row and this column, so we will be left with b1, b3, c1, 3 3 plus here it will be a2 1 3, so total 4, so it will be plus 1 and a3, and then you will be left with this b1, b2, c1, c2, right? Now you expand that, what you will get. So now you know that how to calculate for these order, right? You multiply the diagonal wise, so you will get a1, b2, c3 minus b3, c2 minus a2, b1, c3 minus b3, c1 plus a3, b1, c2 minus b2, c1, right? Okay, so this is what you get for the given matrix. Now let's say it says that if I interchange all the rows with the columns and all columns with the row, right? For example, meaning to say that you get a transpose of it, right? So if you get a transpose, then what will happen? Then all the rows becomes columns, so it will become all rows becomes here a column, and all this you will have b1, b2, b3, and here it will have a3, b3, c3, right? So you see that all rows are now columns here, right? So it means that you have just taken the transpose of the matrix kind of thing, right? So it is the similar way you can get the determinant. You just interchange the row with the column, and then you estimate this value here now. So what we will get from this determinant? Now again, let's here you know that any determinant you can expand either along the row or column, it will value remain. So there we expanded here with respect to row. Now here I can expand with respect to column. No, it doesn't matter, right? Now if I expand it with respect to this, the values should be same as we had seen our previous discussion. So we'll get again here a1, b2, c3 minus c2, b3 minus a2, b1, c3 minus b3, c1 plus A3 B1 C2 minus B2 C1, right? And which is equal to what? It is equal to this, so you can say that it is with respect equal to delta. So it means that now you have a transpose of that matrix. So for example, let's say if the matrix is A, so you get the matrix transpose A dash, and that determinant of A dash is your this delta dash here. So that delta dash is equal to delta. So it means that now, as stated with this property, that if a given matrix you take a transpose of that matrix and take the determinant, so the value will be same, right? So obviously if there is a matrix and its determinant is just the interchange row, so their value should not change, right? So this is one important property related to that. Now the second property is that if any two rows or column of a determinant are interchanged, then sign of determinant will change, meaning that let's say if you have a determinant like this, A1 A2 A3 B1 B2 B3 C1 C2 and C3, right? Now it says that if any two rows or columns are interchanged, right? So let's say if it is your R1 and this is your R2 and this is R3, or any column C1, this is C2 column and this is C3 column, right? So you interchange any two columns, right? Here you interchange it, no, R2 with R3, R1 with R2, RC1 with C2, RC2 with C3. If interchange that, the determinant sign will, the value sign will be changing, right? So let's see how it will change. So let's calculate the first one. So as we already did here, for this one, and we got the value what? We got the value here. This one, right? So let me write that directly. So delta, you got A1 B2 C3 minus B3 C2 minus A2 B1 C3 minus B3 C1 plus A3 B1 C2 minus B2 C1, right? Now let's say that we interchange the column, any two rows or any two column. So for example, let's interchange the first with the third one, right? Let's interchange first with third one. So what will be the matrix? So let's say it becomes a delta 1, right? So that will be looking like how. So this R3 is interchanged with R1, so it becomes C1 C2 C3, and here it becomes B1 B2 B3, and this is as it is, this becomes A1 A2 A3 because it is interchanged, right? Now let's expand it with respect to this, right? So as we saw that you expand either any respect to any row or any column, the value is not going to change. That property we already know from our previous lecture, right? So if you expand it, so let's see what we get. So here now here the index for this is 3 1, this is for 3 2, and this is 3 3, right? So 3 1 will get what? Plus minus, if you take minus 1 to the power 3 plus 1, and A1, and we will get the remaining multiplied. So this they will leave it, so we will get C2 B3 minus B3 C2 B2 C3, right? Similarly you get for the next digit minus 1 to the power 5, I will get the value, and here you multiply with A2, and then you leave this and this, then you get A1 B3 A1, sorry, this is C1, right? C1 B3 minus A1 C3, sorry, B1 C3, right? And the third element would be minus 3 3 6, right? So minus 6 A3, and then you leave this, you will get C1 B2 minus B1 C2, right? Now let's see then what would be the value here, final by A1. You can write as C2 B3 minus B2 C3 minus A2 A1 B3 minus B1 C3 plus A3 C1 B2 minus B1 C2, right? Okay, So now I take common minus from everyone, right? So it will become A1 B2 C3 minus C3 B2 B3 C2 B3, right? Minus this minus is coming from here, right? So it remains minus there because it again here it will be B1 C3 minus A1 A1 B3, and here A3 B1 C2 minus C1 B2, right? Right. So now you compare this this and this, and then you will get delta 1 is equal to minus delta, right? So you see that you interchange the any the row or column, you are getting the negative. So that is another interesting property which you will utilize whenever it is needed, that you interchange any two row column without affecting the determinant, but if you, what would be the impact of that if you interchange that any row or column in the case of determinant, it will just be negative of the same determinant, right? So that's another interesting property. Now let's see that what is the third property here. Any two rows or columns of determinant are identical, then the means all the corresponding elements are same, the value of determinant will be 0. That's interesting, that you can find such kind of property, then you can immediately say that the value is going to be 0. So for example, let's say this is your determinant A. It is let me represent it like this only, it is simpler for me. A11 A12 A13 A13 B11 B2 A21 A22 A23 A31 A32 and A33, right? Now it says that if any two are identical, right? So it would mean that you can have, let's say A11 A12 A13, so corresponding any row. So let's say for row 1 and row 2 it is identical, so it is also A11 A12 A13, and this is not identical, right? So you can just write like this, right? So if they are identical, and we just discussed in the previous property that if you interchange any row or column, the sign will change, right? So it would mean that if they are identical, and if I interchanging this and this, so interchanging this, then it will become what? It will become the same matrix, right? Interchange this will become minus, remains the delta, same thing, right? Because I interchange, then I will just take the minus from the previous property. So it would mean that delta is equal to delta is equal to 0. It means that delta will be 0, right? So you see that utilize the property 2, which says that if you interchange any row or any column with each other, and then it the same determinant will get would be negative of the main determinant. And now utilizing that, if in this property, keeping in mind that property, if any two rows are having the same element, corresponding element, then obviously you can interchange, and it would mean if you are able to interchange, then it will be going to negative, right? So in a simpler way you can say that in such cases you will have a determinant 0, so you don't have to solve it, you just utilize that property understanding. Now the next property, which is property 4, it says that if each element of a row or a column of a determinant is multiplied by a constant, then its value gets multiplied by k. So what it means is that let's say you have a determinant A, it's A1 A2 AB1 C1, let's say A2 B2 C2, or A3 B3 C3, right? Now let's say another matrix where now you multiply with each element of a given row, any row. So let's say this first row, so A1 KB1 KC1, and this remains the same, A3 B3 C3, right? Now let's find out the value for this delta 1. So what would be the value? So we'll just expand with respect to this row. So you have to discard this part, so it will become KA1, and then this will be multiplied, so you'll have B2 C3 minus B3 C2, right? So now you expand with respect to this. So for here it is always plus minus plus, you remember, plus minus plus when you take the sign. And the best way you remember that, first column first row, so when they say ij you have to add, right? So you can remember like that. So this will be kb1, and then you leave this, so it will become a2c3 minus a3c2 plus you expand this kc1, and then you can write a2b1 a2b2, so a2b3 here minus a3b2, right? Now take column full k out, and then you can write a1 b2 c3 minus b3 c2 minus b1 a2 c3 minus a3 c2 plus c1 a3 b3 minus a3 b2 a2 b3 minus a2 b3, right? And now you remember when you expand this thing, this matrix, you will get the same value, right? So you can write k delta. Now you see that now you can write that this matrix, meaning that if you are having a sum matrix ka1 kb1 kc1 a2 b2 c2 a3 b3 c3, right? Then it would be equal to k a1 b1 c1 a2 b2 c2 a3 b3 c3, right? So it means now remember, now again we got a very interesting property here, that in case of matrix when we apply multiply with out with a matrix some constant, then it was getting multiplied with each element in the matrix, right? But in case of determinant, if any row are having multiplied with some constant, then it will be having multiplied with the whole determinant. It's not the every element. So that's a very interesting difference from the matrices here. And also the property that in any row, if you find a common factor multiplied in all the rows or any all column, so you can multiply the whole determinant with the same this constant value, right? So that's another interesting property related to that. And also it would also mean that if you have any two rows or any two column which have a proportional with some common constant, then you can always take that factor out. Or you can say that if there are proportionality, for example, let's say for example here you have some matrix delta which is a1 a2 a3 b1 b2 b3 c1 c2 c3, right? Now you have another matrix delta 1 which is having a constant multiplication. So for example it's a1 a2 a3 b1 b2 b3 and c1 c2 c3. So here it is multiplied in this, right, k. So this becomes this is equal to ka1 ka2 ka3, right? So then you can write this as like this: a1 a2 a3 b1 b2 b3 a1 a1 a2 a3, right? Now you see that now we apply the other property here that this two rows are common, then its value would be 0, right? So it will become 0. So you see that now if any determinant which have any two rows are having proportionality with a certain cost value, then their value will be 0. So that's another interesting property that you this multiplied by k, but here its corollary you can say that sub property with this, that if any two rows are multiplied having the proportionality with each, we get the same value after taking out the constant, and then it makes the two rows the same, then you utilize the other property and then this value will be 0. So here utilizes the two property. One is that each row having constant proportionality, then they will take out, and then you get the two rows are common, and then you immediately say that now its determinant will be 0, utilizing the two property. So for example, you are given to evaluate a matrix something like this: 100, 2, 18, 36, 1, 3, 4, 17, 3, 6, right? So see, you can write it like this. It can be written as 6 into 17, 6 into 3, 6 into 6, right? 1, 3, 4, 17 3 6, right? So it will be equal to what? You can take out the 6 factor common from this row, so it will become 17 3 6 1 3 4 and 17 3 6, right? Now you see this and this row are going to be common, so it will be meaning that value will be 0, right? So you can easily, even if expand and calculate, you will get the same thing. So that's a very interesting property. Now let's say the other important property, which is property 5. If some or all elements of a row or column of a determinant are expressed as a sum of two terms, then the determinant can be expressed as the sum of two or more determinants. Meaning that let's say if you have a matrix like this: a1 plus lambda 1, a2 plus lambda 2, at plus lambda 3, b1, b2, b3, c1, c2, c3, right? So it can be written as like this: a1, a2, a3, b1, b2, b3, c1, c2, c3, right? Plus the other get that lambda 1, lambda 2, lambda 3, b1, b2, b3, c1, c2, c3, right? So that's the interesting property. Like no, in case of matrices, we used to have that each element gets added up, and then you'll have two matrices. But here in any row, if there is a sum, and then you can add up in the case of determinant in the form of two, sum of the two or more determinants, right? So that's again notice the difference between determinant and matrices, and this is how you expand in case of determinant. So I'm not going to prove it, it's just simple. You just have to expand with respect to this R1 here and get the value, and then you will see that value will be sum of these two, and you will get the same value. Then you can say that LHS is equal to RHS. So this is just the simple calculation. You can have a look, but remember the property that how you can expand, and the difference with respect to matrix. In case of matrix, each two matrices addition means that each element corresponding element gets added, but in this case if any row have some addition value, then it can be written as to sum of the two determinants. Now another the interesting property that if each element of any row or column of a determinant, the equimultiple of corresponding elements of the row are added, then the determinants remains same. That's interesting property, and it would be well utilized when you want to find maximize the number of zeros without affecting the determinant value, and then that makes our calculation simpler. So here it says that the operation, you remember that Ri is transformed to Ri plus some constant k Rj, right? RCI transferred to Ci plus kCj in case of matrices. So here we are going to utilize that kind of operation in the case of determinant. So let's say determinant is your a1, a2, a3, b1, b2, b3, c1, c2, c3, right? And some another matrix, you have a delta 1, which is given as a1 plus some constant k, and then you have this c1, right? The r2 k r2, so r1 plus k r2, right? So you can write k c1. Here it can have a2 plus k c2 and a3 plus k c3, right? Here it can be b1, b2, b3, and here it can be c1, c2, c3, right? Where you can see that delta 1 you can achieve by r1 plus k r3. Now utilizing the previous property, how you can write it? Delta 1, you can write delta 1 as a1, a2, a3, b1, b2, b3, c1, c2, c3 plus k c1 plus k c2 plus k c3, b1, b2, b3, c1, c2, c3, right? Now you take it, so this will be your delta like this, plus you take the constant out from here, and then you can write c1, c2, c3, b1, b2, b3, C1, C2, C3. Now you remember that now it have a two rows common, so the value will be 0, so you will get the same value, right? So see how interesting property you got, that if you apply this kind of operation, your determinant value is not going to change. But this operation will help you to find maximum number of zeros, making maximum number of zeros by transforming that without changing, affecting the determinant value, and then you can simplify the equation and you can find the value where it is associated. So that's really interesting property. You remember these 6 properties and it will help you to solve determinants, complicated determinants in much simpler, much lesser time. So that's improve your efficiency to calculate it if you understand it better and you know the property. So this is all about this property. Let's have a quick example and then we'll this section here after that. So for example, let's have a calculation. So let's say you are given A, B, C, C1, C, A, B, right? This is the matrix we are going to estimate for the this determinant, right? So how you can get the maximum number of zeros. So let's say this is your row 1, this is row 2, and this is your row 3. So if you apply the you make it 0 or this 0, so how you can make it? You will easily make, and without changing, affecting the determinant value. So you can be writing that R2 is equal to R2 minus R1, and you can also make it 0, so you can write R3 is equal to R3 minus R1, right? So it is not going to change the determinant value, and then it will mean then delta will become like this. So first row will remain the same, second row becomes R2 minus R1, so it becomes 0, this becomes B minus A, and this becomes C is common, right? So you take C common, so it will become A minus B, A minus B. Similarly you apply here, it becomes 0, here it becomes C minus A, and this will become B common, and you will get A minus C, right? Now you further take B minus A from R2 and C minus A from R3 common, so you will get this will be equal to, you can multiply, this will be out, so it will be multiplied from this row B minus A, and here it will be C minus A, and then you will get 1 A B C. This will become 0, this will become 1, and this will become your minus C. This will become 0, this will become 1, and this will become minus B, right? Now you can easily further expand it. It's easy now. So what you will get? You will get B minus A, C minus A, and this will become minus B, and minus plus C, right? So you will get B minus A, C minus A, C minus B, right? So see how beautifully you have determined utilizing the properties, and you make it very simple. So though it was a very simple, even we could have got it, but not like this factor. It would have taken lots of time, but now utilizing this property, it have made much easier to calculate this kind of thing. So this is all about the properties. Again we'll discuss the application, very nice application for this, and in our next lecture we will discuss about area of a triangle, how you can utilize the determinant to find the area of a triangle if the Cartesian coordinates are given. So we'll discuss that in our next lecture. Till then, thank you.